Okay, welcome back to the course. So, the previous video, we kind of just talked through our data and we came up with a decision tree just by thinking about our data, right? We were trying to find the best questions to ask of the data to more confidently classify the student as a pass or a fail. So in our training data, of course, we know if the student passed or failed, right? So we're trying to classify. If we were to use the tree on future data, then we're trying to predict if the student will pass or fail. So we tried to think of the best question. So how does the training algorithm mathematically determine, right, what is the best question? How does it determine what the best questions are? If you think about, we have a lot of features in our data, so you could have asked a lot of things. You didn't have to ask, does a student have greater than zero failures? You could have asked what, if their mom was a teacher, or if they, drank on the weekend or something like that. You had a lot of choices. So how do you determine what is the best yes or no question to ask? So let's look at some um, pretend splits here, pretend splits of the data. And I'm asking you, which one is better? So this is some question, which we didn't fill out the question. So this is just a pretend, who knows what this question is. But in this imagined scenario, it splits, right? If you look at the training data, all of the rows that answer yes to this question are passes. All of those students passed and all of the students failed. Now, I'm making this up. There's actually no question of our data that splits the data this cleanly, but I'm just pretending. Let's pretend there's something we'd ask of our data. And for all the students in our training data that the answer is yes, all of them passed. For all that the answer is no, all of them failed. Now here's another pretend question. And for the rows that answered yes, well, 5 of those passed and 3 failed. And for those that answered no, 5 passed and 3 failed. So the fail rate or the pass rate is the same in both of these groups. And also, I'm pretending that we only have 16 rows of data. Um, so our data set obviously a lot more, but I'm pretending that of all the data, the 16 rows, 8 of them are in this split and 8 in this other split, and the actual fail ratio is the same. So which one of these do you think is a better split? So I'm sure you're thinking this top one, right? In one question, we have completely divided the data from into passes and fails. This is a great question, right? So whatever this question is, if it were real, this is the question we'd like to ask of any future student. We hope that the same relationship we'd see for future data, and that we could basically ask one question and then have a very confident guess as to if they pass or fail. This doesn't do anything for us, right? The fail rate is the same in the split. So this question gives us really no information at all. The fail rate when we started um, would have been the same ratio. So if you just put these two sets of data together, you have the same ratio of three, what is that? 3/8. So in this case, 3/8 of the students failed. And after you ask this question, you split the data into two sets, but the fail rate is still 3/8 in both sets. So this really tells you nothing. So this is a bad split. This is a good split. So how do we measure that mathematically, right? How do we put a number on this that an algorithm can then optimize? An algorithm could then test all possible splits and determine the one that has the best score, where the score is a measure of how good the split is. So what is that score? Well, um, there's two popular scores that are used. One is the Gini impurity and the other is information gain, uh, or sometimes entropy. Here it referred to as entropy, so meaning the same thing in the information gain or entropy. Um, so the two popular scores are Gini impurity or information gain, and the default one in scikit-learn is Gini impurity. So that's what we will use. You could look up. There's articles written on Gini impurity versus information gain, and there's different pros and cons. But for now, we'll use Gini impurity. So in the next video, we'll talk about Gini impurity. All right, welcome back to the course here. So we left off when we were talking about the Gini impurity score. Now, the Gini impurity score is a score that helps the training algorithm determine which is the best split. What is the best yes or no question for the node. And a Gini impurity score is something that we're trying to minimize. So a score of 0 is perfect. So this is a score of 0. This split actually has a score of 0. And this would have a score greater than 0. So we're trying to minimize it. Now, how do you actually measure the Gini impurity? Well, first, the impurity is actually calculated per leaf. So these would both have a Gini impurity. These would both, and then the split would be the average of those impurities. So how do you calculate the Gini impurity? Well, here's the formula. So it's 1 minus the sum of the squared probabilities of selecting a data point for each class from the leaf. So we're going to step through this. First of all, we only have 2 classes, so we can actually write this equation in a simpler format. This equation will work for multi-class problems, but we only have 2 classes, right? Fail or pass. So let's write this a little simpler. So we can write this as 1 minus the probability of selecting class 1, which we will call a fail. So we'll say 1 minus the square probability of picking a fail from the leaf minus is the squared probability of picking a pass from the leaf. Let's try that. Let's go up here. So remember, this is being applied to training data. So when you apply, it's using the training data to train the algorithm. So when you apply this split to the training data, we can actually count how many rows will be in the left side and how many in the right side. And we, of course, know which of those rows were fails and passes. So for this split, we go over here and we look at the data that would be in this leaf in our training data set. We'd say, okay, so what is the probability of picking a fail? Well, it's 100% because these are all fails. What's the probability of picking a pass? 0, because there are none. So if we go down here and we put that in the equation, we say, okay, well, 1, right? 1 minus the probability of picking a fail squared, which is just 1, because the probability is 100%, which mathematically we say is 1. And 1 squared is just 1, so 1 squared is just 1. The probability of picking a pass is 0, and 0 squared is 0. So the formula is 1 minus 1 minus 0, which is just 0. So this has, both of these leaves have an impurity score of 0, which is perfect, right? So let's calculate the Gini impurity for this leaf. All right, so what is the probability of picking a fail? Well, it's 3 out of 8, right? We have 8 data points, 3 are fails, so the probability is 3/8. The probability of picking a pass is 5/8. So let's go down here and put those in the formula. So 1 minus 3/8 squared minus 5/8 squared equals 0.46875. So we'll just say about 0.47. And because these leaves are really the exact same, right? 3 fails and 5 passes in each, then the Gini impurity is the same in both, in this case. Okay, so that's essentially how the training algorithm determines the best split. So you could imagine, right? You could imagine going through each feature of the training data and asking a question and then determining the Gini impurity. So you could ask, okay, let's split on if the student has more than 0 failures, right? And then no or yes, and you could count the number of passes and fails in each category here. Or you could ask, does FEDU, so father's education level, you could say, does it equal 3, or is it greater than 3, or greater than 2? You could ask if internet, you can say, does internet equal yes, right? Does the student have internet? And then you'd go through all the rows where it's yes and determine the fail pass ratio, or no and determine the fail pass ratio, and then you could calculate the Gini impurity from our training data. Okay, so we understand that. Now let's understand a little more in the next video about how the decision tree trains. All right, I'll see you in the next video. Okay, welcome back. So we have learned about Guinea impurity, and now let's talk more at a high level about how the algorithm uses this, the training algorithm. Well, it tries to find the best split at each level in order. So what I mean is the first thing the algorithm has to do is decide a question to ask of all the data, right? The top split. So what is the first way you're going to split up the training data? Is it on failures? Is it on the go out feature? What is it on? So you could try every single one and calculate the Guinea impurity for each, and then you're going to select the split that leads to the lowest Guinea impurity, right? So that's what you're going to do first. And it's a greedy algorithm, meaning it will always choose the best split it can. So at the top, it's going to choose the best split. Now, of the data that, right, so the first split splits the training data into two sets, here and here. And of that data, you can ask another question, and it will determine what is the best question to ask of this data, right, where Mass is circling the data on the left. The data on the right can also be asked a question, and these don't have to be the same question. So even though these are both on the second level of the tree, so here's the top level, here's the second, these don't have to be the same question. So it will optimize the question at each level here, and it will continue until it has divided all of the data into leaves that are pure. So it will continue to ask questions until it's divided everything into leaves that are pure, even if there's just one data point. So even if it comes down to two data points and it finds a way to split those, these are two data points, one's a fail, one's a pass, and it finds a way to some true or false question that will put one on the fail side and one on the pass side, so they're pure. So you'd have just one fail here and one pass here. It will continue until it can do that, or it runs out of things to split on. Meaning, so this is what I mean by runs out of things to split on. Let's say that we get to a point where there are just two students, and one is a pass and one is a fail. If they are identical in their features, so if they have the exact same feature, right, the exact same value for every feature, then it can't split on anything. It can't separate them. There's nothing it can separate them on. But if there's any difference, it will split them. And because of that, they can overfit. The decision tree algorithm will overfit. So an example is, again, two students, one's a pass, one's a fail. One happens to be 21, the other 22. It will then split on the age at that level. And so I think that probably it's pretty clear how that can overfit. Now we're taking a very small sample size of two students and determining that at that level, we can split on the age and determine if it's a pass or fail. So decision trees are, as we'll continue to see, they are extremely good at overfitting, and that's a problem that we'll have to deal with. And I want to talk through this one more time. You may be wondering, well, why would it wait till two data points to split on the age, right? How does that happen? Well, you can ask the same question multiple times if you want. So this might be a split on the age here, but over here, there might be a split on the age. So you can imagine you can imagine a path of questions that goes, continues until there are only two left and the difference is age. Then it will just split on age down here, even if it's split on age at 10 different areas in the tree. It will overfit. So we will see more of that as we train trees. You're going to see, I think probably just a few lectures, you'll see on our data how you can really get a crazy decision tree that will classify the training data 100% correctly, but then of course it performs very bad on the test data because it's overfit, right? It's splitting on features in the data that are essentially noise and that do not have any value in new data, in the test data, or any new data that you would use the model on. All right, in the next video, we will talk a little bit about how we can prevent overfitting.